Let us begin our lecture. Want to make sure the recording has been started. So we were talking about the properties, table properties, and I have kind of alluded to you that these table properties, let me copy and paste in our slide here, and they will help you to understand what is what are the different types of properties associated with a pure substance. But sometimes the properties are combined. For example, enthalpy has been combined. This is internal energy, this is a flow energy. Flow energy is a unit joules, but over here this is per kilogram. So in order to get this U plus PV, look, P which is pressure, specific volume which is specific one. So unit of P is Newton per meter square, and unit of specific volume is meter cube per kilogram. And this meter square is cancelled by this, and you are left with Newton meter per kilogram, which is joules per kilogram. This is the unit of energy. This is known as the flow energy. Look, when the mass travels, it contains two types of energy due to the internal molecules plus due to the flow. How much flow uh, is there? So when the engineers they thought of whenever you will study one more thing, the mass which carries energy, you will study in later on that enthalpy is just one combined property. When the fluid is flowing inside a tube, then you should know what is enthalpy. It is a combined property, the internal energy plus the flow energy. This is known as the enthalpy. And this column of a pure substance, in this case this pure substance is water, this column is telling us the enthalpy, value of enthalpy at a certain pressure given temperature. Okay, so let's do over here. Yes, now I'm gonna show you how would you read the table. In this slide you will understand how will you read the table. Look over here. First of all, every table has its name. Table A-4 is saturation properties of water under temperature. This is temperature table of water. The A table A5 is the uh, pressure table of water. So usually the first column tells us which is it a pressure table or the temperature table. It doesn't matter, but sometimes it is convenient for us to read the table values if the temperature is given directly. Suppose 90 Celsius. At 90 Celsius, what is the um, boiling or vapor pressure or saturation pressure is just 70.18, and VF liquid line, the volume, specific volume of the saturated liquid and saturated vapor. As you can see, this is higher than this one, this obviously. So you see, this is this is this is VG, this is VG, this is specific volume. The x, this is specific volume at the liquid line, and this is temperature. So this temperature is saturation temperature. So the latent heat is the heat between the liquid line and the dry vapor line. This is latent heat. And this latent heat, this line, look, this line keeps on, the width of this line keeps on decreasing when we go towards the critical point. Critical point itself has sufficient energy that at that pressure and temperature, the liquid suddenly vaporizes. So, okay. And now we go to the next slide here. The example, they are just telling us that uh, how what is this liquid line, this point is given at 90 Celsius saturated liquid and pressure. Look, Over here, this is 70.8183. You will draw a constant pressure line. As I mentioned, constant pressure line are drawn like this. And then this is a constant pressure line. This is a constant pressure. And how would you represent this digit here? This is VF. This is VG. This is VG. Again, telling you everything in detail. Now, if the pure substance is in between the latent heat region, liquid vapor region, suppose very near to the vapor, so you can tell us, Professor, X represents the quality of the liquid vapor region. Okay, there can be a quiz question that do we have quality for this region? Can you type in yes or no? In the superheated region, do we have the quality? Please type in yes or no in your chat box. No, we do not see the quality. Quality um, only occurs inside the latent heat region. So if it is very close to the vapor line, it is the quality. So mass of vapor divided by the total mass. Total mass includes the liquid mass and the vapor mass. So you can, this does not occur inside the superheated region. Okay guys, this is important that you should know what is quality. Okay, quality, the ratio of mass of vapor to the total mass of the mixture from 0 to 1. 0 means liquid, 1 means saturated vapor. Now, if you want to find out the liquid vapor mixture properties, there is a formula. The formula is here that you need it. So, so U equals to UF plus X UFG, H equals to H HF plus X HFG. V average equals to V plus. So these are the formulae which we will implement in our problems. Now this is a pure substance, not water, but R134A. This is a gas which we use in our air conditioning HVAC system, and the properties are given as such that at at this temperature, what is the saturation liquid vapor mixture? So for water, so for R134A, so this is, you see, all this is sub F. This is all sub G. Okay, guys. So if I say, what is the property over here? You will say, Professor, this is the formula for any property inside the latent heat region. And if I ask you, okay, guys, can you find out enthalpy at this same point? You will say, yes, Professor, HF plus X HFG. And so, for example, okay, HF is given, HG is given, so you can find it out easily from the table. Have you understood the how to find out the properties inside the latent heat region? Please type in yes if you understood this liquid vapor mixture region. Taylor says yes. Carter says yes. Sarah says yes. Good job, guys. So I'm glad that you have understood the concept. It's not difficult, but we will understand the concept, and this is important for our problem solving skills. You see this table, it is this is just a small portion of the table A6. So table A6, you can in this region you can find out the properties. So What is superheated vapor? So superheated vapor, it is not difficult to find out. First of all, you will see if the suppose the the temperature saturation uh, over here, the temperature over here, it is 100. Suppose this is 100 Celsius, and the constant pressure is constant. And then if the temperature is above 100, if the actual temperature of the substance is above, I would say if it is above 100, then it is inside the superheated vapor region. This is how you will find out whether the substance is lying in the superheated region or inside the liquid vapor mixture region, or on the dry line, or on the liquid line, or on the compressed liquid. The usually this portion, it is usually below boiling point. Okay, so this is important. For the superheated vapor, we have a different table. So for that one, I want to show you from one cut and paste A6, table A6. Let's go to the book and table A6. If you just copy and paste inside this notebook, yes, you see, this is table A6. And first of all, you will locate the pressure. Which pressure do you want to find out the values at? This is a pressure. And the first line for any table, the first line is the same line given in the saturated region. That then the next line goes to the following temperature, like higher temperature. Okay, guys, I'll teach you once the time comes how to read the superheated. We will solve some problems. At that time, I will explain it further. How would you find out the values? Okay, as you can see, the higher temperature should be higher, specific volume should be higher. Don't worry about a lot of property, but it's okay to understand. But at least one thing you should keep in mind: the temperature, actual temperature of the substance should be higher than the saturation temperature, and then it would be falling into the superheated vapor region. Okay, let's go to the next slide here. So let me show you. Okay, now this is telling us that what if the how do you identify any state point inside the compressed liquid region? Okay, let me explain. For any property, you will read the properties at the liquid line. Suppose this is also considered as the same property, UF equals to, or I would say U equals to, approximately equal to U sub F. So if I want to tell you that this is the temperature which is 75, less than the boiling point. The boiling point is 151.83, but your liquid is at 75. It is inside the compressed liquid state. Okay, the actual temperature is less than the saturation temperature, and then the liquid will be lying inside the compressed liquid state. And then but the properties you will consider from the liquid line. Okay, guys, have you understood this concept? The property, you don't have to further accurately find out the property. There is no it is very convenient for, it's approximately almost the same. There might be some table which are telling us the actual. So now this table is completely telling us the this is the cut and paste of the table which I've been telling you from the beginning of the lecture. What are the properties? Specific volume, internal energy, enthalpy, entropy, and the expressions are sub v, small v is the representation for the specific volume, small u, specific internal energy, small h, specific enthalpy, small s, specific entropy, all these values. And this is the temperature table for water. Similarly, we have a pure substance refrigerant R134A for a HVAC system. Okay, now we go to the next slide. But before I go to the next slide, let's do one problem. Let's do one problem so that you should be having some knowledge about how to find out the properties in the table. So let's do 3, 6. Okay, let's do this problem. Let us complete this table together. So the question is complete this following table for water. So let us complete. So only look in the first row, it is given 200 pressure and the quality is given. When the quality is given, can you tell me what phase it is in? It is compressed liquid, liquid line, liquid vapor mixture, dry vapor, or superheated vapor. Where this quality is telling us. Can you guys write down where this state point is located? It is inside the liquid vapor mixture. Very close. Like 70% is vapor mass of the vapor inside the container. Okay, now let's go to the table. So I'm going to open the book and see the table is table. I would look into the pressure table A5. A5 is the pressure table and look for 200 kilopascals. So I'm gonna just use this. Can you guys see the table? Yes. Okay, let's find out. At this pressure table, I'm looking at 200 kilopascals. So this is temperature. Look, 200 kilopascal. I will draw a rectangle, and then this rectangle, all these values are under focus, under my focus. So I need T temperature. Can you tell me, please type in the chat box what is temperature, saturation temperature at 200 kilopascal. Can you type in the chat box? Good. Sarah is correct. Taylor is correct. Good job, guys. So this is my answer for the first row, 120.21. This is correct. I'm glad you guys have understood how to write. Let's find out h. Since h is not given directly, but we know this formula is very helping to find out the values inside the liquid vapor mixture. Liquid vapor mixture. So I want to focus. I want to focus on this on these three columns. Okay. So why on this column? Because this first column is HF. So I'm gonna write down F 504.71 plus zero point 0.7 times HFG. Look, this value is 2201.6. 2201.6. Do you guys see that? So if you do the math and help your professor, the professor will be happy. I got 204.5.83. And one thing you should notice that this should never ever exceed this dry uh, vapor line value because it is less than this line. So Hg would always be Hg was always be greater than other H values inside the liquid vapor mixture. Okay, guys, no. So the answer is that's correct answer 2045.83. 2045.83 kilojoules per kilogram. This is the unit. Okay, guys. So I'm gonna write it down here. 2045.83. Now, phase description: liquid, vapor, mixture. Now let's consider this one. 950. So I'm gonna draw a line. Oh, 950 is not in this, so I have to cut and paste another one. So let's do another cut and paste from the table, which includes the pressure at 950. Now you will help your professor at 950. I'm gonna draw the rectangle around the 950. This is the value. So you can help your professor. What is the saturation temperature at 950? Sarah says 177.6. That's correct. Good job. So let's do it. Oh, am I missing the second one? Oh, 177.66. I think I missed this one, but I will come back, or maybe you can do it by yourself. This is zero. Look, zero means it is exactly on the U sub F line, liquid line. So HF, we need to have HF over here. So what is HF here? 752.74. This is our answer, 752.74. And this is a liquid saturated line. Okay, now over here I am going to show you the temperature table. This is pressure table. Okay, this is pressure table. The pressure table. I want to show you temperature A4 table, and name is A4. And for that I want to cut and paste 140. So let's do this one. I'm gonna just cut and paste here 140. So now we have done this part. So I'm gonna draw the rectangle around 140. This is the temperature table. Okay, so the benefit is that it is convenient for us to find out the values through the temperature table rather than pressure table. Okay, at 140, what is the saturation pressure? Can you type in the chat box? What is the saturation pressure? P61. That's correct. P61.53. Now this value for H enthalpy is given. You have to find out the equality. So let's do it. We know this formula. You remember this formula has been given to us. Okay, that's good. So let's go and see. You have to see whether H is greater than Hg or less than. If it is greater, then it's a superheated vapor. If it is less, this is in the liquid vapor mixture. So I'm gonna draw the rectangle around the. So look, what is Hg over here? It is 2733.5, and our H is less than 273, so it is inside the liquid vapor mixture. You see, guys, liquid vapor mixture, because our H is 1800. Our H is 1800 less than Hg, therefore it is inside the liquid vapor mixture. So we can find out the answer for X, H minus HF over HFG, and it equals to 1800 minus HF. It is 589.589.16. This is 1800. Okay, guys, divide by 2733.5, and that will give you the answer. You can calculate the answer. Let me try to do it in my calculator. So 1800 minus 589.16. Okay, guys, this is divided by 2733.5. 0.443. So this is quality 0.443. Can I write on here 0.443? So we have done these three rows. That's good. Have you understood these three rows? Please type in yes. If not, then ask your professor. Please type in yes if you have understood these three rows. And let's go to the next row. The next row is 80 and 500. So yeah, it is over here. Look, 80 is given directly here. Now, what is the saturation pressure? Here the saturation pressure is 47.416. 47.416. So look, if this pressure, which is a saturation pressure, which is at the dry vapor line. So let me show you over here. This is our liquid line. This is our dry vapor line. This is our constant pressure line. Okay, guys, if this pressure is, and as you go up and up, the pressure increases. This pressure is, suppose this is P2, so pressure P1 is greater than P2, and this is the critical pressure, which is very high. So this is just, this is temperature, this is specific one. So let's see, at 80 the pressure is 47.416, and our pressure, look, it is 950 kilopascals. It is much higher at this pressure. So um, at this temperature, 80 Celsius, 80 Celsius, pressure is, so it is falling inside the, let me check one thing, 950 kilopascals. I'm sorry, I'm mixing, this is 500. Sorry, so this is 500 kilopascals. This is 80 Celsius, and this is our 500. So this pressure is higher, our pressure is high. Is this inside the somewhere, I'm not sure, this is this pressure. So what I'm gonna show you this, if the pressure is higher than the saturated pressure, then this is the superheated region. So let's go ahead and see the value inside the table for the value. So I'm gonna show you the different table. A dash 6, A dash 6 will help me. 0.05, yes, this one, I found it, this 81. So I'm gonna show you. So point 500, let me copy this one here and show you how would you find out the unknown values from the superheated region. So we are talking about 80, which is the temperature here, and points, okay, 500 kilopascal, 500 kilopascal, 500 kilopascal